In our previous video, we played with a little abstract puzzle, the Towers of Hanoi puzzle, and analyzed exactly how long it takes to solve it. Now we're going to start to move towards more realistic problems in computation, which connect to all sorts of scientific fields, and we'll find that it's useful in many cases not to try to analyze things exactly, but instead just to understand them in a coarse-grained way, and in particular to understand how they scale with the size of the problem. Complex systems is full of scaling theory. Often we meet power laws as well as exponentials. We want to understand how things change as a function of the size of the system. And we're going to do that with a notation called BigO. First, I need to tell you how computer scientists think about a problem. So, to a computer scientist, an actual problem isn't just a particular puzzle, like, can you tour this particular graph, visiting every node exactly once? A problem is an infinite set of puzzles, an entire family of puzzles, or examples, or computer scientists often say instances. So, for instance, even chess is just a finite puzzle. You can solve chess completely in order one time. What in the world does that mean? Well, there is an astronomical number of different positions that the chess pieces could be in on the board, and yet it is only a finite number. So there could be a book the size of the galaxy that tells you what to do in every situation. And for that matter, if you ask me the yes or no question, does white have a winning strategy in chess? Well, I can tell you that there is a very short computer program which gives you the correct answer. It's either this program, print yes, or this program, print no. I'm not sure which it is, but it's one of those, unless it's a draw. On the other hand, if we generalize chess beyond the traditional 8x8 board to an n-by-n board, a board that could be of any size with all kinds of extra pieces on it, now you're talking. Now a computer scientist would say, that is a real problem, and now we'd like to know, how does the amount of effort we need to play this game perfectly grow with the size n? How does it scale? I should mention that we're usually interested in computation time. That's the most common computational resource to worry about, because frankly, it's the thing we usually run out of first. But there are other resources that matter to us. For instance, in very data-heavy applications, like say astrophysics, where we have billions of images being downloaded from a telescope, or genomics, it might be memory that we run out before we run out of time. And so we're often concerned with how much memory it needs to solve a problem as well. There are even other branches of computer science that think about other resources. For instance, suppose that I have part of a problem and you have the other part, and we need to solve it together. Then we might want to quantify how much communication we need to carry out between the two of us in order to jointly solve that problem. So really, theoretical computer science is interested in any limited resource, time, memory, communication, energy, hardware. For all of these resources, we want to know how the amount of them we need grows or scales with the size of the problem. So now we're going to talk about algorithmic scaling and this thing called BigO. So the whole idea of BigO is to release us from worrying too much about the constants. My computer might be half as fast as yours, so it takes me twice as long to solve things, but that's not really what we care about. What we care about is whether both of us are having to do an exponential amount of work, or whether there's some brilliant insight which lets us both solve the problem pretty quickly. So let me introduce you to this BigO notation. If I say that f of n is BigO of n cubed, it means that when n is really large, f of n scales like n cubed or less. So it grows at most as fast as n cubed grows, maybe with some constant hidden inside that BigO. Now, notice that like physics, like the study of scaling in cities, like many branches of complex systems, We're asking this question in terms of the limit of large n. It's because we really want to understand the asymptotics here. It's not hard to solve little problems of size n equals 5 or n equals 10. What matters is how this function grows as n gets really large. So there's a formal meaning to this if you're mathematically minded. F is big O of g if there are constants c and n naught such that whenever n is bigger than n naught, whenever n is big enough, f is less than or equal to c times g. Frankly, you don't need to worry about this formal definition too much. It's just saying that when n is large enough, f is bounded by some constant times g. So the shape of f somehow lies below the shape of g, and it grows at most as fast. Another way to put this is that the ratio, f over g, doesn't blow up. It doesn't tend to infinity as n grows. It might be 1, it might be 10, it might be 100, but it doesn't blow up. Here's an example. I might have some problem with some algorithm, and its running time might be kind of complicated. N log n plus 10 to the 8th times n squared plus n cubed over 1,000. Well, the important part about this is that it's big O of n cubed. And it's worth pausing here for a moment. Because that 10 to the 8th there in front of the n squared means that for fairly small values of n, that's the biggest term, the 10 to the 8th times n squared. But when n is really large, that n cubed term will take over even though it's being divided by 1,000. So asymptotically, in the limit of large n, it's that last term, the n cubed term, which will tell us how the function grows. There are more notations which come in handy in computer science, which frankly we will use only rarely, but you ought to know them. Computer scientists use big omega to mean the reverse of big O. If f is big omega of g, it means that f grows at least as fast as g, which is the same as saying that g is big O of f. So I might want to say something like, I really need n to the 10th time to solve this problem, and in that case the running time would be big omega of n to the 10th. Another way to put this is that the ratio f over g doesn't tend to 0. Yet another notation is big theta. Well, that means they grow in pretty much the same way. F is big O of g, and g is big O of f. They still might differ by a constant. The ratio f over g, again, it could be 1/10, it could be 10, but it's neither going to 0 nor going to infinity. So f and g have essentially the same shape, the same scaling. Finally, occasionally we want to say that something actually is a lot less than something else when n is large, and for that we use little o. F grows more slowly than g. So for instance, if you have an algorithm which runs in n cubed time, and I am seeking a much better, faster algorithm, I want to know, is there one which runs in little o of n cubed time? All right. So for instance, going back to our example with these three different terms, n log n plus 10 to the 8th n squared plus n cubed over 1,000, we can say a couple things about it. It is big theta of n cubed because, again, in the limit that n goes to infinity, it's that third term with the n cubed in it which will really control the scaling of the function. It's also little o of n to the 4th because when n is large enough, it's much less than n to the 4th.